Okay, so again, just to summarize, we have that dy is the estimated change in y, whereas delta y is the actual change in y. And the way that we find dy is you're going to find the derivative, you're going to evaluate it at a given x value. That x value is going to be given for you. And then you're going to multiply that times dx, which is also going to be given to you or easy to find. So you find the derivative, you plug in the x value, you multiply it times dx. That's our estimated change in y. How do you find the actual change in y? Well, this is where you just plug in the new x value minus the original x value into whatever function you're dealing with. That's your actual change in y. So again, as long as our change in x is small enough, our estimated change in y dy should be equivalent or close to delta y, the actual change in y. So again, here's how we're going to find the actual change in y, delta y. You evaluate the original function at one value, you evaluate it at the new, and then you subtract them. So let's look at an example here. It says comparing delta y, the actual change, and dy, the estimated change. It says find the value of dy, the estimated change, when x equals 2 and dx equals 0.01. Notice we've used a very small value for the change in x, so hopefully our estimated change is close to our actual change. We have the function f of x equals x to the fourth. It says compare this with the actual delta y, change in y, when x equals 2 and delta x equals 0.01. So let's first look at dy, our estimated change. To find our estimated change, the first thing we do is find the derivative. The derivative of this would be of x to the fourth is 4x cubed. So now we're going to evaluate that at our given x value, x equals 2. So we find that f prime of x would be 4 times 2 cubed, which is 32. Now what we want to do is find dy, and the way we do that is we do f prime of x, which we just found to be 32, times delta x, or dx, which is our change in x. So again, our f prime of x value here when we plugged it in was 32, and our change in x value, which is our dx, is 0.01. So that's giving us a dy is 0.32. That is our estimated change in y. Let's go ahead and compare this to the actual change in y. How do we find the actual change in y? Well, we need to consider the 2 points. The first point, I'll call it x1, that's when x equals 2. And then x2 is the new point. The new point would be x plus that dx value that we had. So this would be the point 2.01. X plus that change in x, whatever we changed it in. So what do we do to find our change in y? Well, we're going to plug in those two values. So we're going to find f of 2.01, and we're going to subtract of that f of 2. Let's go ahead and plug that into the original function, not the derivative. So that'd be 2.01 raised to the fourth power minus 2 raised to the fourth power. So we have 2.01 raised to the fourth minus 2 to the fourth. Put that into your calculator, and I'm getting the actual change in y is 0.322. Notice it is extremely close to the estimated change in y. So using the derivative in this case would have been a nice estimation for the actual value. Remember, scale this up 1,000 times, and you're talking about something that we could use to estimate cost functions, profit functions, revenue functions, changes in, right now, growth rates for the COVID virus. These estimations could be used, and you could compare what's the estimated versus the actual and see if the derivative gave us a good estimation. Again, the reason why this was a good estimation was because our change in x was so small. So let's see what this next part's talking about. It's talking about marginal analysis. It says differentials are used in economics to approximate changes in revenue, cost, and profit. Let R of x be the total revenue for selling x units of a product. When the number of units increases by 1, so when it increases by 1, that's what we're saying our dx and our delta x is 1. The change x is delta x equals 1, and the change r is delta r equals f of x plus delta x minus f of x. So this is the actual change. What that's saying is plug in the new x value, plug in the original x value, and subtract them. And then what they're saying in the second part is that's approximately equal to the derivative, the differential dr, which is dr dx times dx. Okay, so what this is saying is we can use differentials to estimate the change in revenue. Notice that they're doing the change in 1 unit. So our dx, or delta x here, is 1 unit. So let's read this first approximation here, or first example here. It says, using marginal analysis, the demand function for a product is modeled by p equals 200 minus x for 0 is less than or equal to x is less than 200, where p is the price per unit in dollars and x is the number of units. Use differentials to approximate the change in revenue and sales from the increase of 89 to 90 units. Compare this with the actual change in revenue. So what we're wanting to do here is we're wanting to calculate dr, the estimated change in r using the derivative, and we're actually wanting to calculate delta r, which is the real change in revenue as well. First, I notice it's 89 to 90 units. That's the change of 1 unit. So delta x is the same thing as dx is 1 in this case. That's what our change in x is going to be. Now I also notice that they gave me the price demand function, and I'm actually wanting to look at the revenue function. So I need to remember that the revenue function is price times quantity, which means you take the price demand function, which was 200 minus x, and you multiply that times x, the quantity. I'm going to write this in descending order. So I have that my revenue function is equal to negative x squared plus 200x. Okay, so that's my revenue function. All right, so how do we find dr, the estimated change in revenue, the differential? What do? Well, the first thing that we need to do is we need to find the derivative, r prime of x. So r prime of x, pretty simple here, would be negative 2x plus 200. And now I need to evaluate it at the original given x value. So I need to evaluate it at x equals 89, the first x value, x equals 89. So when I plug in 89 here, I'd have r prime of x equals negative 2 times 89 plus 200. Let's see what we get. Plug that in your calculator. I'm getting a value of 22. So r prime of 89 is 22. And now we're going to use that to estimate what would it be for 90 units, the sale of that 90th unit. Okay, so the way that we find dr is we take that r prime of 89, and then we multiply that times the change in x. Here again, we're just estimating the 90th unit, so our dx is just 1 unit more. Dx is just 1. So we take r prime of 89, which was 22, we multiply that times dx, which in this case was 1. So our estimated change in revenue is an increase of $22. Our estimated change in revenue is an increase of $22. So that's from the sale of the 89th to the 90th unit, is I should sell that unit for, my revenue should increase by $22 between the sale of the 89th and 90th unit. Well, let's find out what actually really did happen. So the way we do this is we plug the two numbers into the original revenue function and we subtract them. In other words, what we want to find is r of 90 minus r of 89. Just plug those into the actual revenue function. So this would be negative 90 squared plus 200 times 90. I'm going to take whatever that value was, and I'm going to subtract off negative 89 squared plus 200 times 89. Throw that into your calculator. Be careful with your parentheses in this one. And I'm getting the actual change in revenue was, I'm getting $21. So our estimated change in revenue was an increase of $22, and our actual change in revenue was an increase of $21. Because our delta x, or dx, our change in x was so small, just 1 unit, we can see that the estimated change in revenue, dr, the differential, was very close to the actual change in revenue, delta r.